Good evening, everybody.
Good evening.
This is Professor Ayorinde. Yes, this is Professor Ayorinde welcoming all of you to the last online review session for the fall 2013 semester. I particularly want to welcome all of you coming in on a Sunday night, especially on a Sunday night that is snowing and a lot of sleet out there. Of course, that simply tells us that one of the advantages of using the online session, because you guys do not have to go in the snow or sleet in order to join this session. So anyway, I do want to welcome all of you to today's session. In today's session, we are going to review for the final exam that is scheduled for Tuesday, December 10. The exam will start at 6:30 p.m. and will end at 8:30 p.m. So this is a 2-hour exam. Once again, the exam is scheduled for Tuesday, December 10, starting from 6:30 p.m. I do notice that we have a lot of students have joined us today, and just in the interest of time, I will acknowledge all of you during the course of this session. So right away, let us go ahead and start the session. What I want to do, I want to start with question 18, and then hopefully we are able to cover most of the questions from 18 to question 41. If there is any particular question any one of you want to ask us to do, just send me a text message. If we have enough time, we might want to do that. Okay, so let us go to question 18. Okay, America, can you go ahead and read this question?
Which one of the following reactions of cis-2-butene is not stereospecific? A. Hydrogenation treatment with hydrogen over platinum metal. B. Acid-promoted hydration, parentheses, treatment with aqueous sulfuric acid. C. Bromination, treatment with bromine gas and CHCl3. And D. Bromohydrin formation, treatment with bromine gas over water.
Okay, very good, and thank you. Okay, so what this question is testing here is actually testing a variety of concepts. One, it is testing your knowledge of the reagents and also testing your knowledge of nomenclature in addition to your knowledge of reaction mechanism. So what we have here, they say which of the following reaction of cis-2-butene, in other words, they want us to use cis-2-butene to react with each one of these reagents here, and they are asking which one of these reactions is stereospecific. So right away, you need to know what stereospecific means. Stereospecific simply means that during the course of this reaction, you only form one particular stereoisomer. Only one stereoisomer is formed. Okay? So that is what stereospecific means. Okay, so let us now take a look at these reactions. So we have cis-2-butene. Of course, you need to know the structure of cis-2-butene, which is this here. And then you say, and then you are asked to give, to tell whether the reaction with hydrogen and platinum, which we refer to as hydrogenation, whether that is stereospecific. Now, you need to know here that hydrogen in the presence of a catalyst, this is what we call a cis addition reagent. This is a cis addition reagent, or sometimes you may refer to it as a syn addition reagent. Now, what does that mean? What that simply means is the two hydrogen atoms will be added to the carbon-carbon double bond from the same side of the molecule. Okay, so let us see what the product will be. Let me use a green color here for hydrogen. So you have hydrogen coming in, adding to the carbon-carbon double bond. Okay, hydrogen comes here, and hydrogen comes here. Okay, and then it pushes down this hydrogen here, and also this methyl coming at us. And this hydrogen here going away from you. Similarly, on this side of the molecule, you have hydrogen being pushed down, going away from us, and the methyl coming at you, or will also push down. So now you have this. Okay, so what you have here, we have added the two hydrogen atoms from the same side of this carbon-carbon double bond. So therefore, we say this is a cis product, cis addition product. Okay, and as such, this will be called a stereospecific reaction because we are only forming a particular stereoisomer. If you take a look at this here, is that clear to all of you? If it is clear, give me a happy face. Okay. Okay, good. So therefore, we say this will be stereospecific. Okay. This will be stereospecific. Now let us take a look at. Okay, let us take a look at C. I will come back to B later. Let us take a look at C. What would that do? In C, you have bromination. Okay, so you have bromine. And in chloroform as a solvent, this chloroform here is only a solvent. Okay. Now, this reagent here, bromine by itself, is what we call a trans addition reagent. In other words, it will add two bromine atoms across the carbon-carbon double bond such that the addition will be on a different side of the molecule. So one bromine could come here, the other bromine could come from the bottom, and while the first one comes from the top. So therefore, let us look at what we get. We have bromine here, coming from the top, and this other bromine coming from here. Okay, so now we have hydrogen is pushed down, and you have your methyl here, and here also you have hydrogen is going away from you, and the methyl is coming at you. So what have we done here? We have added this reagent. What it does is to add two bromine atoms across the carbon-carbon double bond such that the two bromine atoms will be added from different sides of the molecule. So therefore, this is a trans addition product. Okay? So this is a trans addition product. Therefore, we are only forming the trans product. So the question is it stereospecific or non-stereospecific? Anybody has an idea? Would this be a stereospecific reaction? Just give me yes or no. Would the bromination be a yes, very good, excellent. So bromination would be a stereospecific reaction. So we say yes to this. Okay, now let us go to D. Does anybody have an idea what? Yes, somebody asked a question for me. Go ahead. Erin, go ahead. Erin, do you have a question for me? Okay. Is this reaction the same as bromine? Yes. Yes, this same, okay, the question Erin is asking, instead of using a chloroform as solvent, can you also use carbon tetrachloride? Yes, that is correct. You could also use carbon tetrachloride, which is this here, also as solvent. So it is the same reaction. Okay. Okay, so now let us go to D. Does anybody have an idea whether D will be stereospecific or not? If it is stereospecific, say yes. If it is not, say no. Anybody has an idea? For D. Yes, I see all kinds of yes. Okay, very good. All good. Okay, so let us see that. That is correct. The bromine water, in other words, when you have bromine and water reacting with a carbon-carbon double bond, what does it do? What this reagent does here is to add a bromine and an hydroxy group, in other words, bromine and OH across the carbon-carbon double bond, and this reagent is also a trans addition reagent. Trans addition reagent. Which is to say that the bromine and the hydroxide will be added to the carbon-carbon double bond from opposite side of the molecule. Okay? So what are we going to get? So if we have bromine here, then the hydroxide will be here. Okay? So once again, this will be a trans addition product. So, and that is why this is also a stereospecific reaction, because we are only forming one particular stereoisomer. Okay? So now we've dealt with A, C, and D. Now let us take a look at B. Of course, at this point, all of you now know that the answer to this question must be B. If we say A, C, and D are stereospecific, so therefore the answer must be B. The question now is, why is the answer B? Okay, let us take a look at it. Why must the answer be B? Okay. Anytime you have a carbon-carbon double bond and you have dilute sulfuric acid, which is generally H2SO4, in water, and that is why they call this aqueous. In other words, you have sulfuric acid in water. Anytime you have sulfuric acid in water, indeed, any kind of acid in water, and you have a carbon-carbon double bond, most likely that reaction will go through the formation of a carbocation. Because the first thing that happens, you have a proton, say from the hydronium ion, because you have a dilute acid. This is your hydronium ion. Okay, this combination here will give you hydronium ion, which is this here. This right here. Okay, so this is your hydronium ion here. So the first thing that happens is that the pi electron in the carbon-carbon double bond will act. In this case, we could say it will act as a base because it is going to grab this proton here and thereby releasing the bonding electron between the hydrogen and oxygen. Notice my arrow, right? This arrow here says that we are moving 2 electrons. And then what do we get? We get this. We get a carbocation. Because this hydrogen here, this is the hydrogen here. Let me use a green pen. This hydrogen here, it is now this hydrogen. So now on this carbon, you form a carbocation. And of course, you now have water here released. Now, the moment you form a carbocation, this carbocation, the hybridization is an sp2 hybridized carbon. sp2 hybridized carbon, which means that this here, this part of the molecule is what we call trigonal planar. Meaning that this part of the molecule is flat. So therefore, what is going to happen here, the water will now come in to act as a nucleophile. It could either come from the bottom or it could come from the top. Okay? Now, if it does any one of these, there is no reason to believe that it will come from the top any faster than it will come from the bottom, because this part of the molecule is flat. Therefore, you are going to get 2 products in which you have to get this, or you could get this. Or you could get this, in which now you have hydrogen is going away. So in this case, we are getting these 2 products here. Okay? So we do not have a chance to make a particular stereoisomer. So we are going to get both of the isomers. So therefore, that is why the reaction of sulfuric acid with a carbon-carbon double bond, it is not a stereospecific reaction. Okay? It is not a stereospecific reaction. And that is because we are going through the formation of a carbocation. Is that clear to all of you? If it is, give me a happy face. Okay, very good. Okay, so let us go to the next question. Okay. Okay, Masha K., can you read this question for us?
Which carbocation is the most stable?
Okay, thank you. Yes, which carbocation is the most stable? You have the choices here: methyl, primary, secondary, or tertiary. This question is in a way related to the last problem that we just solved. Now, so what will be the answer to this? Which is the most stable carbocation? D. Excellent. So we do not need to spend too much time on this. The answer here is D. The more substituted the carbocation, the more stable the carbocation. So tertiary carbocation is more stable than secondary, primary, or methyl. Very good. So let us go to the next one. Okay, Kiara Wallace, can you read this question for us? Okay, I think maybe Kiara may be having problem with her mic. Danuchik Gelin, can you read the question for us?
Which of the following forms the most stable carbocation?
Okay, thank you. Okay, so the question here is asking which of these following is the most stable carbocation. Once again, this is also related to the last two questions. Okay, does anybody have an answer to this? Methyl iodide, ethyl chloride, 2-bromopropane, and 2-iodo, 2-methylpropane. Okay, all of you got that right. D is correct. D is correct, okay. Okay, does anybody know why D is correct? Does anybody know why D is correct? Okay, let us look. More stable, yes. Okay, from tertiary carbocation, exactly. That's what I wanted to hear. It forms a tertiary carbocation. And the rest of these here do not form tertiary carbocation. So if you look at this, 2-iodo, 2-methylpropane. So we have this molecule here, 2-iodo, 2-methylpropane. So we are making an assumption here that this molecule will be losing the iodide, and in so doing, you are going to form a tertiary carbocation. This is a tertiary carbocation. Now, another way I could ask you this question, I could also ask you this question by asking which of the following substrate, is best for SN1 reaction. Okay, that I could also ask you the same question in that same way. In other words, asking which of these substrates here would be best for SN1 reaction. Of course, the answer would be D, because in an SN1 reaction, the first thing that you get is the loss of the leaving group to form the carbocation. So therefore, if you have a substrate that will give you a very stable carbocation, then that would be very good for SN1 reaction. Okay? Okay, so let us go to the next one. Okay, let us see here. Robin, can you read this question for us?
Which of the following will react as a nucleophile?
Okay. Okay, which of the following will react as a nucleophile? Okay, the question that I have for you guys, what is a nucleophile? What is a nucleophile? Okay, let us see. As lone pair of electron, okay, very good. As lone pair of electron, okay, a nucleophile will have lone pair of electron. Yes, that is correct. A nucleophile will have lone pair of electron. It could also have pi electron. A nucleophile could also have pi electron. Okay, so very often, any species that has lone pair of electron could act as a nucleophile, and sometimes it could also act as a base. Okay, the same thing with a carbon-carbon double bond. The pi electron in a carbon-carbon double bond could also act as a nucleophile, because you are going to use the pi electron here as a nucleophile, and those same pi electrons could also be used as a base. Okay, so keep that in mind. Okay, given that explanation, which of these following is a nucleophile? Do you guys have an answer to this? Ammonia, hydrogen, methane, and borane? A. Okay, excellent, excellent. A. Guys, A is correct. Okay, why is A correct? Anybody has an idea? Why is A correct? Let us look at the structure of A. Why is it correct? Of course, it has. Because if you take a look at this question again, it is actually testing your knowledge of the valence rule, the octet rule, which we did in chapters 1 and 2, because it has lone pair of electrons. Very good. Okay, if you look at this here, nitrogen is in group 5 of the periodic table, which is to say that nitrogen has 5 valence electrons. So valence electrons. So nitrogen has 5 valence electrons. Now, if you look at this molecule here, which is ammonia, if you actually ask yourself, how many electrons actually belong to nitrogen in this molecule? How many electrons actually belong to nitrogen in this molecule? Does anybody know? How many electrons actually belong to nitrogen in this molecule? Anybody has an idea? How many electrons actually belong to nitrogen in ammonia? Okay, keeping in mind that this bond is 2 electrons. Okay, very good. Okay, this is 2 electrons here. One belongs to nitrogen, the other belongs to hydrogen. The same thing here, and the same thing here. So somebody said 3 electrons. Very good. 3 electrons. Therefore, if you look at ammonia, okay, nitrogen needs 2 more electrons in order to have its full valence and the usual valence that it will normally be expected to have. Plus, if you also look at this molecule, based on the octet rule, you know that nitrogen therefore needs 2 more electrons in order to have an octet of electrons around it. And that is why we have this right here. Okay? Even though it is not written here, nitrogen does have a pair of non-bonding electrons right here. Okay, but if you take a look at hydrogen, that is not the case. Okay, hydrogen only has 1 valence electron, so therefore, in its natural state, and if you look at nitrogen in this molecule here, that's 1 electron here, 1 electron here, so it's happy. Okay, now the same thing if you take a look at methane. Okay, carbon has 4 valence electrons. It is in group 4 of the periodic table. And if you look at this molecule here, you have 4 electrons actually belonging to carbon. In addition to that, it has a full complement of the octet of electrons surrounding the carbon right here. So carbon is happy. No non-bonding electron. Okay? So carbon will not be the answer, so that is out. So this is also out. Let us look at our borane. If you look at borane, it's a fairly interesting molecule. You have here boron attached to 3 hydrogen atom. Okay, just as in the case of ammonia right here. But the difference here is, if you look at the periodic table, boron is in group 3. So boron actually, in nature, it only has 3 valence electrons. And if you look at this molecule here, that we call borane, actually boron does have 3 electrons that actually belong to it, which is therefore satisfying the natural valence requirement for boron. However, from the point of view of the octet rule, this molecule is very unstable, because what does it tell us? Boron does not have an octet of electrons surrounding it, and so what that means is boron will have a vacant p orbital. Boron will have a vacant p orbital, and as a result of this, boron will be very willing to react as a Lewis acid. Keep in mind, a Lewis acid is any species that is capable of attracting electrons. Because boron has this vacant p orbital here, it will be willing to attract a pair of electrons. So you will find that boron very often is considered a Lewis acid. So anyway, in this particular question here, this is not the case. So the answer here is ammonia. Okay, ammonia will act as a nucleophile. Okay, let's go to the next one. Okay, I think we did that, a lot of that not too long ago, so let us go to this one here. Okay, I want to spend just a little time on this. Sean, can you go ahead and read this question for us? I know we did this in class already.
This mass spectral data MZ120M 1057743 belongs to a compound that has.
Okay, very good. So we did this already several times already. So, but the reason I want to bring this up again, there is one concept that I forgot to tell you in class. I do want to take the time now to tell you about that particular concept. This molecule here, the molecular ion is 120. That ion has M/Z 105, 77, and 43. And based on what we discussed earlier in class, this molecule will be this right here. It will be that molecule. Okay, at least one possibility. It could be this here. Okay, okay. What do I say? A propyl and a propyl. Okay, so very good. Okay, so this could be this. It could also be this. Okay, this fragment here is 43, and also this fragment here is 43, and of course this fragment right here, this is 77, okay, and this fragment here, if we lose a methyl, This is 105, and the same thing will happen here. If we lose this metal here, that could be 105. Now, why do I bring this up? There is another concept that I forgot to tell you in class. Very often, mass spectrometry, we could use mass spectrometry to tell us the presence of some element in an organic molecule. For example, we could use mass spectrometry to tell us whether we have a bromine atom, a chlorine atom, or a sulfur atom in a given molecule. And how does that work? If you take a look at nature, let's take, for example, bromine. We have two major isotopes of bromine in nature. We have what we call bromine 79, and then we have what we call bromine 81. Okay? Now, bromine 79 in nature is, let us assume it is 100%. If you take a sample of bromine in nature, 100% bromine, and relative to that, we will say the bromine 81 is about 98%. Okay? So what does that mean? If I have this, supposing I have this, bromine is here. Since mass spectrometry actually looks at molecules, not an aggregate of molecules, it looks at specific molecules. So we are going to have a molecule that has bromine 79 here, and then we are going to also have another molecule that has bromine 81. So if you take a look at the mass spectrum of this compound, let us see here, this part of the molecule at this point will be 119. Okay? So if we add 79 plus 119, I believe that would be 198. Okay, we say that is your molecular ion. Then if you take the other isotope, the molecule that has bromine 81, so that would be 81 plus 119, and that would be 200 atomic mass unit. So this we refer to as M+2 ion. Okay, so if you take a look at the spectrum of this compound, you will see this. You see an ion at 119. At 198. And then you see the M+2 ion at 200, right here. This is the M+2 ion, right? This is the molecular ion here. And the ion at 200 is your M+2 ion. So anytime you take a look at the mass spectrum of any molecule, you see an M+2 ion, which is almost the same intensity as your molecular ion. What that is telling you is that that molecule contains a bromine atom. Okay? Of course, all of the other ions will still be here. The 43 is still here. Okay, you have an ion at 119. Okay, so but the point to be made here is, if you take a look at the mass spectrum of a compound and you see a molecular ion, and then two masses away, you see another ion, which is almost the same intensity, then you know that you have bromine in that molecule. Now the same thing could be made of chlorine atom also. With regard to chlorine, in nature, you have chlorine 35, and then you have chlorine 37. Chlorine 35 is about, if you say that is 100% relative to chlorine 35, relative to chlorine 37, then the chlorine 37 will be about 33%. Okay? So if we go back to this molecule again, and we have chlorine here, the mass spectrum of that molecule will look like this. You have, okay, we have chlorine, that is 35 plus 119. Okay, that would be 154. So then in the case of chlorine 37, 156. So what are you going to see? You see a molecular ion at 154, which is your molecular ion. Then you see an M+2 ion, which will be about 1/3. Okay? That's your M+2 ion, which will be about 1/3 of the molecular ion. If you see that relationship in the mass spectrum of a compound, what that tells you is that you have chlorine in the molecule. Of course, the rest of the ions are still here. 43 will be here. Okay, and 119 will be there. So all of the other ions will still be there. But the point to be made here is, anytime you look at the mass spectrum of a molecule and you see this kind of relationship, molecular ion, then the M+2 ion, which is 1/3 or 33% of the molecular ion, then you know you have chlorine in the molecule. Now the same thing also applies to sulfur. In the case of sulfur, the M+2 ion is only 5%. In the case of sulfur, you have sulfur 32. If we say this is 100%, then sulfur 34, the other isotope, will be only 5%. So in this case, if you see an M+2 ion that is only 5% of the molecular ion, then you know you have sulfur in that molecule. Anyway, that is why I brought that up, because I forgot to actually tell you this particular aspect of mass spectrometry. This is a very important one. Okay, so let us go to the next question. Okay. Ronel, can you go ahead and read this question for us? Okay, maybe Ronel is having problem with her mic. Okay, Makiva, can you read this question for us?
What is reactive intermediate in the conversion of T-butyl alcohol to T-butyl chloride by treatment with HCl?
Okay, thank you. Okay, so what is the reactive intermediate in the conversion of T-butyl alcohol to T-butyl chloride by treatment with hydrogen chloride? Okay, this question is also related to the first one we did. Okay, so testing your knowledge of nomenclature is also testing your knowledge of reaction mechanism. Anytime you have hydrochloric acid and you have an alcohol reacting, what that is going to do, you are going to form you are going to form generally carbocation, particularly if you are starting with a tertiary alcohol. Okay, so let us look at tertiary butyl alcohol. So we need to know the mechanism of this reaction to answer this question. Okay, tertiary butyl alcohol okay, in the presence of HCl, the question is, which of these carbocations will be formed? Does anybody know what the answer to this will be? Will it be butane? That is not a carbocation. Tertiary butyl anion, tertiary butyl carbocation. Oh, I almost gave that. I think I gave that away already. Butyl radical. What will be the answer? C. Okay, C is the answer. You are going to form a carbocation. So how does that happen? In this case, you have an alcohol, and then you have an acid. The oxygen of the alcohol, of the hydroxy group, will be acting in this case as a base, because it is going to give this pair of non-bonding electrons to this proton here, pulling this proton away from the acid. Notice my arrow here, and we are going to break the hydrogen-chlorine bond. And in so doing, what do we have? So you form the protonated alcohol, plus your chloride is here somewhere. Now, the reason why this happens, because eventually, this is going to be an SN1 reaction. In an SN1 reaction, of course, you know that you are going to form a carbocation. But in this case, hydroxide is not a good leaving group. Hydroxide not a good leaving group. So in order for the hydroxide to leave, we use the acid as a catalyst to protonate the oxygen. And now once you do that, you now have water will now be a good leaving group because water is stable. So now it will now break away. Okay? It will now break away, and when that happens, you form a carbocation in this case. Okay, so once again, the reason why you need this acid here is to protonate the hydroxide, thereby making the hydroxide a good leaving group in form of water. Now, water is gone. Now, the chloride will now come in as a nucleophile, okay, to bond to the carbocation. Okay, so this is a case of an SN1 reaction. This is an SN1 reaction. Okay, it is a substitution reaction, but in this case, we are going through the formation of a carbocation. Anyway, so the answer to this is tertiary carbocation, which is tertiary butyl carbocation. That is the question they want us to answer here, and that is this right here. Okay, so this is the right answer. Okay, is there any question on this? Okay, no questions. So let us move on. Okay, now let us begin to look at the reagents. Okay, let me start all over again. Now, if I have not called you today and your mic is working, I do not know how many of you whose mic are working. Can you pick up the mic and read this question for us? Okay, let me call on
Which is the best set of reagents to carry out the following reaction?
Okay, thank you. Who was that again? Can you read the question again?
Which is the best set of reagents to carry out the following reaction?
Okay, that's Lauren Kibet. Thank you. Okay, so you say which is the best set of reagents to carry out the following reaction? Okay, now we are getting to reagents. What do we have? What would be the answer for this? Which of the best set of reagents to carry out the following? Which would be the answer to this? Anybody? We have water in hydroxide, mercury acetate, followed by sodium borohydride, borane followed by hydrogen peroxide. Okay, and then water in the sulfuric acid in dilute acid in water, of course, sulfuric acid in water. Okay, so what would be the answer to this? Okay, anybody has an idea? Okay, by the way, this would be, what type of reaction would this be? Would this be an hydration reaction? Or would this be an addition reaction? Or, addition reaction or substitution reaction? Okay, very good. Addition, anti-Markovnikov addition. Addition of what? Anti-Markovnikov addition of what? Somebody say excellent. Okay, so we are adding the elements of water. That is correct. Anti-addition. Okay, anti-addition of water. Anti-Markovnikov addition of water. Okay, at least the elements of water across the carbon-carbon double bond. Okay, in this case, hydrogen is going here, and the OH is going here. That is what we have here. Okay, so what will be the reagent? What will be the reagent that does that? Which of these reagents will do that? C. Very good. Okay, excellent. So this is a case of knowing your reagents, folks. You need to know your reagents. Borane followed by hydrogen peroxide in hydroxide. What it does is to add the element of water, which is hydrogen and hydroxide, across the carbon-carbon double bond in an anti-Markovnikov fashion. In other words, the hydrogen will go to the carbon that contains less hydrogen, and the hydroxide will go to the carbon that contains more hydrogen. That is the anti-Markovnikov addition. Okay. Supposing we use this. Supposing we use this reagent here. What would that give you? Supposing you use that reagent, what would that give you? Would it be Markovnikov or anti-Markovnikov addition of water? Exactly. This would be Markovnikov addition of water. That is what that reagent would do. Markovnikov addition of water. Okay, now supposing we use D, what does this reagent do? Okay, would that be a Markovnikov addition or anti-Markovnikov addition of water to a carbon-carbon double bond? Okay, is that okay? It's a Markovnikov, very good. So this will also be a Markovnikov addition of water across the carbon-carbon double bond. Okay? So therefore, both the dilute acid and mercury acetate followed by sodium borohydride, they do form the same type of product, which would be Markovnikov addition. Okay. On the other hand, the borane followed by hydrogen peroxide in base would be anti-Markovnikov addition of water. So in this case, the answer is C. The answer is C. So this is just a case of knowing exactly what your reagent will do. A, water in base does not react with a carbon-carbon double bond, at least as far as you guys are concerned, okay? Okay, so let us go to the next one. Okay, I think we did all of that, so we don't need to worry about it. We did all of that earlier. Okay, that's nomenclature. Okay, let us see here. Emeka, can you go ahead and read question 30 for us?
Provide the most likely mechanism for the following formation.
Okay, thank you. Now, we are now getting to reaction mechanism. Does anybody know what type of mechanism is this? Let me give you some choices. Is it SN1? Apparently, it must be substitution reaction, okay, or SN2. What will it be? Will this be an SN1 reaction or SN2 reaction? SN1 reaction, very good. What makes you think this is an SN1 reaction? That is correct. It is correct, it's SN1 reaction. What makes you think it is tertiary substrate? Exactly. Anytime you have a tertiary substrate, and you are giving a substitution reaction, you are giving, a substitution reaction, then what should come to your mind right away, this must be an SN1 reaction, okay? Okay, so now they tell us to give the reaction mechanism. Very simple. Let us do that. Let us do that. Okay, in this case, we do not need an acid catalyst to make this reaction work, just as in the case of the alcohol that we did earlier, when I told you this was an SN1 reaction. Because in this particular instance here, the bromine will live as a living group. Is this a good living group? So what does it do? It simply just breaks away in an heterolytic fashion. Heterolytic. Okay, cleavage. Okay, and once it breaks away, it now forms, in this case, a tertiary carbocation. Okay, so this tertiary carbocation, you have this here. Okay, at this point, this cleavage here, this part of the reaction mechanism, this is what we call the rate limiting step. In other words, this is the step that determines the rate of the reaction. That is the rate limiting step. Okay. Now, so therefore, and also because the rate limiting step only involves the substrate, the rate equation for this reaction becomes K, which is some constant, multiplied by the concentration of the substrate. Let us represent the substrate by Rx. Okay. Okay. So the rate equation only involves the substrate right here. It doesn't involve anything else. And that is why we call this an SN1 reaction. That is where the 1 comes in. Okay? 1 stands for unimolecular. Okay, so once you form this, now the nucleophile now comes in. In this case, the water, which is the reactant here, come in and now react, attack this, use a different pen, attack this. Okay, once it does that, we now have okay, because water is using a pair of non-bonding electrons, this oxygen is positively charged. So at this point, what happens now? The bromide here now comes in to now react as a base. Notice here, a species that is capable of reacting as a nucleophile is also capable of reacting as a base. So now, and whenever a species reacts with a proton, we say it is a base. So what does it do? It comes in to grab the proton. And that is why we say at this point it will be acting as a base. Okay? Releasing this electron here. And that is how you get this product right here. Okay? And of course you also get hydrogen bromide. Okay? And that is the reaction mechanism. Notice, if you are told to write the reaction mechanism, you have to indicate which step is the rate limiting step. In this particular reaction, if you are also told to write the reaction energy profile for this, if you are told to write the reaction energy profile for this, it will look like this. This is energy here. Reaction energy profile. Okay, this will be the reaction progress. Okay, now what would it look like? You have the reactant coming here, go through a transition state, and that transition state will collapse to form an intermediate, and then finally another transition state to form the product. Okay, so you have here, so you have the substrate, okay, to form the transition state, and this is the rate limiting step. Okay, this energy that you need here, this is what we call the energy of activation. Okay, and this particular reaction, therefore, because the product here, the final product is this, and this is your carbocation, and this is another transition state. So we have two transition states here. Let us create, this is 1, 2, and this is the first one. Okay, the fourth transition state, according to what I've drawn here, is actually the rate limiting step. And you therefore say this reaction here, because the product is more stable than the starting material, you say this is an exothermic reaction. You say this is an exothermic reaction. Okay, exothermic reaction as opposed to, for example, if you have a reaction that is endothermic, what does that mean? That means that if you have okay, let me leave that. If you have an endothermic reaction, what that essentially means is that you have a reaction in which you have the starting material goes here, go to transition state, and then it collapses. Okay, you notice here the energy of the product, Okay, this is your starting material, and this is your product here. Call this product. Because the energy of the product is higher than the energy of the starting material, we will refer to this here as an endothermic reaction. This will be an endothermic reaction. Okay? Okay, so now we have given the reaction mechanism for this. So in this case, okay, folks, if you can hear me, give me a happy face. Okay. I think I lost my internet connection there for a second. Okay, I'm glad that you guys can hear me. So let me, okay, very good. Okay, now, so anyway, so I was, before I lost the internet connection, I was going to tell you that this is a classic SN1 reaction mechanism. Okay, so let us go to the next one. Okay, Masha K, can you go ahead and read this question for us?
Provide the missing reagents for the following sequence of reactions.
Okay, thank you. Okay, so we should be able to do this very easily. Okay, we need to go from the carbon-carbon double bond. Now we want to add a carbon atom across the carbon-carbon double bond to form a cyclopropane molecule. What reagent do we need here? Anybody? Does anybody have an idea? What reagent do we need to go from here to here? Okay, you want me to help you out? There is what we call a Simmons-Smith reagent. And that reagent is, okay, very good. You guys got it. Very, very good. That is your Simmons-Smith reagent, which is, okay, diiodomethane, okay, in the presence of zinc amalgam. Zinc amalgam is just a mixture of zinc and copper, okay? So this is the reagent that you need to add a carbon across the carbon-carbon double bond. And that is what you have here. So in essence, you are forming a three-membered ring system. Okay, very good. So that is the reagent for that. About B, now we want to go from B, we want to form the acetylene molecule here, or a carbon-carbon triple bond. Okay, so what reagent do we need for this here? What reagent do we need for this? Anybody has an idea? Okay, 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 keep trying. Keep in mind we need to form a new carbon-carbon bond. Oh, exactly, excellent. Acetylene with sodium with potassium hydroxide will give you acetylide. So this is the reagent you need. Sodium acetylide, and we could get the sodium acetylide by reacting acetylene with sodium amide or potassium hydroxide. Okay, so that gives you the acetylide, and then don't forget that this carbon here is this carbon right here. So what are we doing here? We are doing an SN2 reaction in which the acetylide will be acting as a nucleophile, attacking this carbon here, and the bromine will be a good leaving group. So this will be an SN2 reaction, okay? Because keep in mind, for SN2 reaction, your leaving group must be attached to a primary carbon atom or sometimes a secondary carbon atom. So this is a classic case of an SN2 reaction. Okay, so this is the reagent that you need right here. Okay, about C. For C, we are going from a carbon-carbon triple bond to a carbon-carbon double bond. Okay, somebody asked a question here. Would saying for B, oh, no. You cannot use the Gilman reagent for that. Okay, oh, I see what you're saying. Yeah, Gilman reagent with carbon-carbon. Okay, let's see. Yeah, you might get to be able. Okay, using a Gilman reagent, you might be able to get away with that. But the best thing to use is to use the acetylide right away. In other words, because we make let's stick with the acetylide. Okay, we don't want to confuse anybody at this point. Let's stick with the acetylide right here. Okay, about C. We want to go from a carbon-carbon triple bond to a carbon-carbon double bond. Okay, what reagent do we need? What reagent do we need? We want to go from triple bond to a double bond. Anybody has an idea? Okay, Lindlar, hydrogen in the presence of Lindlar. Okay, excellent. So here we want to use for this part here, we want to use hydrogen, okay, in the presence of Lindlar catalyst. Lindlar catalyst, okay, that will take you from a carbon-carbon triple bond to a carbon-carbon double bond. And also, since in this case, we do not have to worry about stereochemistry, whether cis or trans, we could also use, in this particular instance, sodium in ammonia. Okay, that is different from sodium amide. This is sodium in ammonia or lithium in ammonia. Okay, that will also take this particular carbon-carbon triple bond to this carbon-carbon double bond. Okay, now let us do the last one here. D, this here. What are we doing? What are we doing in D? Anybody has an idea? What are we doing in D? Okay, adding water, hydration, OH and F, exactly. Markovnikov addition. Okay, Markovnikov addition of water, excellent. So what reagent do we need for that? Markovnikov addition of water, that is correct. So what reagent do we need? Okay, mercuric acetate. Okay, very good. Okay, here you have to say you are going to use step 1 and then followed by sodium borohydride. Okay, that is the way you need to indicate that, sodium borohydride. Okay, so you start with mercury acetate. Okay, mercury acetate in water, and then you follow that up with sodium borohydride. So that will give you the addition, Markovnikov addition of water across this carbon-carbon double bond, in which case the hydrogen goes here, because it is a Markovnikov addition, in which the hydrogen goes to the carbon that contains more hydrogen, and the hydroxide goes here. Okay, the hydroxide in this case goes to the carbon that contains less hydrogen. You could also use sulfuric acid in water for the same reaction. Okay. Okay, so let us do, we spend about 1 hour, 15 minutes. Let us do one more question and then we call it a day. Let us see here. Okay, let us do this question here. Okay, let's see. Let me call on, okay, Danuchika, can you go ahead and read this question first?
Provide a mechanism for the following transformation.
Okay, thank you. Okay, let us do this and then we'll call it a day. Okay, so what do we have here? We have bromine and water. So we have bromine and water. What does this reagent do? Anybody has an idea? What does this reagent do? We need to know what that reagent will do. Bromine and water, or sometimes it could be chlorine and water also will do. Okay, add bromine and hydroxide across the carbon-carbon double bond. Excellent. That is what this reagent will do. Now they tell us to write the mechanism for this. What happens here? Let us write the mechanism for this. The first thing that happens is similar to the mechanism of bromination of carbon-carbon double bond, in which case you have bromine. The bromine moves as close to the carbon-carbon double bond as possible, and in so doing, you are going to create what we call a temporary dipole with this part, this bromine here. You could imagine that this bromine here has a temporary negative charge, a partial negative charge, and this other bromine here has a temporary partial positive charge. And that is because of the proximity of this bromine molecule to this rich electron cloud right here. Okay, so what happens? As a result of the polarity of this bromine-bromine bond, this pi electron comes here, attacks this bromine here. Okay, before we do that, let me also let you know that keep in mind that you have bromine does have non-bonding electron surrounding it all over. Okay, and while that is going on, this bond will break. That bond will break. As that is also happening, this non-bonding electron on bromine will attack this carbon here. Okay? So all of these are happening at the same time. And so therefore, what do we have as the intermediate? We form this. So we form what we call a bromonium ion. We form what we call a bromonium ion. Okay. Now this bromonium ion here, ordinarily, if you do not have this hydroxide in this molecule as part of this molecule, what will normally happen is that the water that is here will now attack the bromonium ion to open the bromonium ion, okay, and therefore you form your bromohydrin. However, since this molecule also contains an hydroxide with all these non-bonding electrons, guess what happens? Okay, keep in mind we need to explain how we form this product. So now, this hydroxide now comes here, attack this. Because whenever you are supposed to give a reaction mechanism, what you want to do is to write a reaction that explains the product that you obtained. Okay, so what we want to do here is to write a reaction mechanism that will explain how we got this product right here. Okay, so once we do that, now we get this. Okay, now we have this here, CH, CH2, CH2, okay, then the CH2 here, then the here, this here, plus, okay. So now the oxygen is protonated. Notice this here attacks this, and so we got this right here. Okay, and of course, we also have this bromide here that was released when we did that, when we did the initial bromonium ion formation, will still be here. Okay, so what happens? That bromide now comes in. Instead of acting as a nucleophile, it will now act as a base to pull this, to grab this proton here, thereby releasing this bonding electron to oxygen, and that is how we form the product. And that is how we go to here, and that is how we go to right here. And in the process, of course, you form HBr. Now, keep in mind, the reason why this happens is because we have this OH in this molecule. If you did not do that, if there was no OH in this molecule, what you will normally obtain would be a bromohydrin. For example, if you have, keep in mind, if you have a carbon-carbon double bond, okay, imagine that this, okay, just similar to this carbon-carbon double bond. Okay, so we have this. If I just do this here, bromine and water, okay, the first thing that happens is the formation of the bromonium ion, which is right here. And then the water now comes in, attacks the bromonium ion, and then you form your bromohydrin, which is a trans addition of bromine and OH across the carbon-carbon double bond. The mechanism will be similar to this. Okay, the mechanism will be similar to this. The difference now is the water will now be acting as a nucleophile instead of the hydroxide that was in the original substrate. Okay, is there any question before we leave? Okay, folks, I will stay behind for another 5 minutes. I will turn off the recorder, and those of you who may want to ask me a question off the record, so it will not be recorded, you could do that after I turn the recorder off. So, folks, enjoy the rest of your evening, and I will see you tomorrow. Okay, so at this point, I am going to turn the recorder off.